Hello, this is Dr. Webb. In this video, we're going to be talking about Jacobians, although probably it should be pronounced Jacobians because it's named after a German mathematician named Jacobi and has nothing to do with British Jacobians or Jacobites or things relating to King James I in any way. But we'll leave that aside for right now. So really this is talking about how to do change of variables inside of integrals. So let's go back to single variable integrals. This is, usually we call this U substitution. And so if we wanted to integrate this right here, we've all been trained to do U substitutions on this. And in this case, the U substitution we would make is we'd set U to be x squared. And then we all know after that, we're supposed to take the derivatives of both sides of this. Du is equal to 2x dx. And then we notice that there's an x dx right here. And so if we divide by 2, get rid of that 2, then we know that we're supposed to replace this x dx with du over 2. And so this integral becomes cosine of u, du, the bounds become 0 and pi over 2. And the whole point is that this is a much easier integral to do than the original integral. Okay. And so really what we're doing in this process right here is we're trying to figure out what's supposed to come of this d of x. So d of x, its technical name, it's the measure. For one dimension, it's kind of measuring length. And when we do this change of variables, going from lengths in terms of x to lengths in terms of u, it changes how those lengths are, how long things are when we do that change of variables. And so this calculation in red is really doing the translation of lengths from x into u. Okay, and so we're going to need to do the same sort of thing when we do this in higher variables, except instead of worrying about lengths, we're going to be worrying about areas. Okay, so let's look at this integral. So we're trying to integrate y squared minus x squared over the region, where the region is enclosed by the lines x plus 1 equals 1, x plus y equals 1, x plus y equals 5, y minus x equals 2, and y minus x equals 4. So let's try and draw this out. Okay, so x plus y equals 1, that's the same thing as y is equal to 1 minus x. And so that's, if this is 1, this is looking at a line with slope minus 1. So roughly like that. Similarly, x plus y equals 5. That has y-intercept 5 and slope minus 1. So that's going to go down, look like that. Y minus x equals 2. So this has y-intercept 2, but its slope is going to be positive 1. And then y minus x equals 4. Let's choose a different color for it. It has y-intercept 4 and slope positive 1. Okay, so the region that's bounded by all of these is inside that square right there, that rectangle. But this rectangle is sort of twisted. It's not parallel to the axes at all. And so if we go through and think about how we would do this in, from what we've been doing in terms of double integrals, we'd have to break this up into a lot of smaller integrals to take care of this. And that seems kind of nasty. So what would be great is, since this already is a rectangle, It'd be great if we had some way to kind of turn our axes to make this easier. And so really that idea of twisting these axes to get this righted, really what we're talking about there is doing a change of variables. And so in this case, the change of variables that we'd want to do is this change of variables here works really well. So if we let x equals u minus v over 2 and y equals u plus v over 2, well, look at what happens when we do x plus y. So x plus y is going to turn into u minus v over 2 plus u plus v over 2. So I have the minus v and the plus v. Those are going to cancel themselves off, and so then I have u over 2 plus u over 2, which just gives me u. So the line x plus y equals 1, that's going to turn into u equals 1, and x plus y equals 5 is going to turn into u equals 5. Okay, and so then what about y minus x? Well, y minus x, so that's u plus v over 2 minus u minus v over 2. And so we can distribute the minus sign. And now we have u over 2 minus u over 2. And so those u's cancel. And we're left with v over 2 plus v over 2, which is just v. So our other two lines turn into v equals 2 and v equals 4. Right? And so our original rectangle on its side suddenly has turned into this side right here is corresponding to u equals 1. The other side is u equals 5. And the other two sides are v equals 2 and v equals 4. And so now in terms of u and v, this is a nice rectangle exactly in the right way that we want to do it. And so these will make the bounds for this really nice. Okay, so same thing as before when we do the u substitution, we care about what happens to dx. Here we have to care about what's going to happen to dA as we change our area from going in terms of x and y into in terms of u and v. Okay, so we need to calculate what dA should be in terms of u and v. And so similar to what we did at the beginning when we started talking about we talked about doing double integrals, we have to think about what is the area that's cut out when we increase u and v by a little bit. So that increase in area, we call that delta A, created when we increase u by delta u and v by delta v. Okay. And so precisely what I'm talking about is, in this case, let's say this point is, let's say this point is x naught, y naught. And so we'll call that x u naught, comma v naught, y u naught, comma v naught. Right? But we know that x is equal to u plus v, u minus v over 2. So this is going to be u naught minus v naught over 2. This is u naught plus v naught over 2. Okay. Now we're going to increase u by a little bit. Okay. And so if I add delta u to the two u coordinates, what are we going to end up with? Well, we're going to end up with a new point u naught plus delta u over 2 minus v naught over 2, comma, u naught plus delta u over 2 plus v naught over 2. And so this is our increase by delta u. And then what happens if we increase delta v? Okay, let's make some space to draw this because this is going to be going down. So let's draw it. So this is talking about this point. We're going down to say this point right here. And so this point is what we get when we change the v's. And so this would be u naught over 2 minus v naught plus delta v over 2, comma, u naught plus v naught plus delta v over 2. Okay. And so again, the first one, this is, we're kind of thinking about adding delta u over here. Second one is we're kind of thinking about adding delta v. And then you can see that these are then, if we join these together, these are two sides of a parallelogram. And so in total, if we added u and v, we'd create, that's our delta A. Okay. And so if you think we're going from the point u naught minus v naught over 2, comma, u naught plus v naught over 2 to u naught plus delta u over 2 minus v naught, comma, u naught plus delta u over 2 plus v naught over 2. Well, what really is this vector right here? Well, the vector going from this point to that point is precisely, subtracting one from the other, you're getting delta u over 2, comma, delta u over 2. Okay, on the other hand, what is this vector right here? Well, again, if I take this point and subtract off that point, well then for that vector, that's going to be, so I have minus delta v over 2, positive delta v over 2. Okay, so whatever delta u and delta v are, these are the two vectors representing the change, and then delta u, delta A, the change in area, then is going to be the area created by the area of this parallelogram with the sides that are these two vectors. Okay, so delta A equals the area of the parallelogram with sides delta u over 2, delta u over 2, and minus delta v over 2, delta v over 2. And we've done this problem before, how to get the area of a parallelogram. And so if you remember, this area here, delta A, well, we could get this through a determinant. And so since these are only in two variables, we just put in zeros for the z components. And so this would be delta u over 2, delta u over 2, 0, minus delta v over 2, delta v over 2, 0. When we multiply these out, delta u over 2 minus delta v over 2, delta u over 2, delta v over 2. There's my k's. Okay, so when we do this, that's my j. We want the absolute value of this. So we're going to go through. We've got lots of zeros there, so that gives me a 0. That gives me a 0. That's giving me a delta u over 2 times delta v over 2 in the direction of k. Going in the other way, this is giving me minus delta u over 2 delta v over 2 in the direction of k, and then zeros. And so putting these together, this is the length of, I have 2 delta u over 2, or I have delta u, delta v over 4, plus delta u, delta v over 4, and this is all in the direction of k. Well, k is just length 1, this is a scalar, and so we just add these together, and we get delta u, delta v over 2. And so that's our change of area. So there's another way to think about this determinant, and it turns out that when you're doing area of a parallelogram in R2, because of these zeros right here, it turns out just to be the determinant of that submatrix right here. And so let's see if we can clear this route out. Write this a bit more simply. And so another way we could have done this is delta A is equal to the determinant of delta u over 2, delta u over 2, minus delta v over 2, delta v over 2. Now, 2 by 2 determinants, this is a bit easier. So this is going to be delta u, delta v over 4, minus, but then there's another minus sign, delta u, delta v over 4 again. And so, again, this turns into delta u, delta v over 2. And so that's what delta A is going to turn into. So compare this to, if we did this in terms of x and y, recall that delta A in terms of x and y is just delta x times delta y. Okay, and so this is sort of saying that area in terms of u and v is half as much as area in terms of x and y when we change u and v by a little bit. Another thing I want to note, if you recall, our change of variables are x is equal to u plus v over 2, y is equal to x is equal to u minus v, sorry. And y is equal to u plus v over 2. Well, this delta u over 2, this is equal to the partial derivative of x in terms of u times delta u. This partial u over 2, this is equal to the partial derivative of y in terms of u, delta u. Similarly, this minus delta v over 2, you can think about this as being the partial of x in terms of v times delta v. And that delta v over 2 you can think of as being the partial of y in terms of v times delta v. And later on in the video, we'll talk more about this connection to these partial derivatives. But you can double check that those that those match up nicely. Okay, so we have our delta A. Delta A is 1/2 delta U times delta V. Okay, so then if we're going through and thinking about forming the integral, then we have to think about what happens as we take the limit as delta U and delta V go to 0. And so that's what's going to give us our dA. And so when we convert our area in terms from x and y into u and v, we have to multiply everything by 1/2. Okay, so dA is 1/2 du dv. Okay, so if we go back to our original integral, where we're integrating over these lines, I didn't write the lines back in, but you remember what they are, where r is looking like a box like this. Well, when we convert it in terms of u and v, well, y squared minus x squared is turning into, well, we're just plugging in the change of variables for those. Our bounds r turns into these nice bounds for, in terms of u and v, where our u's are going from 1 to 3, our v's are going from 2 to 4. And then last but not least, accounting for area, we had to multiply du dv by 1/2. Okay. And so I wrote this, we're integrating in terms of u first instead of v. Obviously we could swap those. If we swap the two integrals, we could swap and turn it into dv du, and we'd have exactly the same thing. And then on the inside, we can do a little bit of work on this. This actually simplifies nicely. And so this all boils down to this very sensible, very nice integral to do. And so this is sort of the power of doing change of variables here, where this is a whole lot nicer integral to do than originally we'd have to cut r up into 3 or 4 pieces and fit them all together to do it. Okay, so what about making change of variables in general? Right, so specifically we're talking about, we're going to replace x with some function of u and v, and we're going to replace y with some other function of u and v. And so we're going to call what x turns into x of u comma v, and what y turns into y of u comma v. Okay, so again, the most important thing to figure out is what happens to our area measure. So what is going to happen to dA when we change things in terms of u and v? And so we're going to think about it in exactly the same way as before. So if we have some point where the x-coordinates start off at plugging in u naught v naught into x, the y-coordinate starts at plugging u naught v naught into y. And then we have to think about what happens when we increase u by a little bit. So let's draw that out over there. And so we get some new point, x u naught plus delta u, y, forgot my v part, comma v naught, y, u naught plus delta u, comma v naught. Okay. And so if you look at figuring out what this vector is going between these 2 points, well, what this vector is going to be is x of u naught plus delta u comma v naught minus x of u naught v naught y of u naught plus delta u, comma v naught minus y of u naught v naught. Okay, so if you look at this, this is starting to look, this difference here and this difference there, which is rather ugly, but I think you can figure out what it's supposed to be. This is looking rather similar to the definition of partial derivatives. And so in fact, if what it's missing is dividing by delta u on the bottom, or instead we can think about we've multiplied it by delta u. And so this right here we can think of as being the partial of x in terms of u. We know it's the partial of x because it's our x functions. And we know that it's in terms of u because we're just increasing u between them. And then because there's no denominator there, we're multiplying by delta u to get that denominator, to cancel off that denominator. And then similarly, from here, this is y of y naught plus delta u comma v naught minus y of u naught comma v naught. So this is becoming delta y over delta u. And again, there's no denominator there, so we're multiplying by delta u. Okay. Similarly, if we look at what happens when we increase the v's, and so this is becoming some point x of u naught v naught plus delta v, y u naught plus v naught, u naught comma v naught plus delta v. This vector is, we can think of as being delta y. Delta x over delta v, partial of x in terms of v times delta v, partial of x, partial of y in terms of v, delta v. Okay? And then we complete these two sides. And we have our change in area cut out by these. Okay, so again, next slide we'll clean this up. So delta A is about equal to the area of, sorry for the typo, of the parallelogram with sides delta x u, delta u, delta yu, delta u. So this is coming from going from u naught to u naught plus delta u. And then partial of x in terms of v, delta v, partial of y in terms of v, delta v. This is coming from v naught going to v naught plus delta v. Okay. And so again, we have this 2 by 2, we have a parallelogram. We can use a 2 by 2 determinant to figure out the area. And so this delta A is approximately the absolute value of this determinant. And to do the determinant, we're going to multiply those two sides and then subtract off the product of those two sides. And if you can see, they both, each of them has a u, a delta u and a delta v. This one has a delta u and a delta v. And so doing that out, we end up with this nice little formula of partial of x, partial of u, partial of y, partial of v, minus partial of y, partial of u, times partial of x, partial of v, absolute value of that times delta u, delta v. Okay, and so we can pull the absolute value just on this part right here because we're kind of assuming that delta U and delta V are always positive. Okay. And so again, when we take the limit as delta A goes to 0 or delta U and delta V go to 0, this is going to turn into this nice dA is equal to this factor right here, du dV. And so what this factor is telling us about is this factor is telling us about how area is changing when we move from xy to uv. And so that's the factor there. Okay, and so we're going to call this determinant, we're going to give it a fancy name. This is the Jacobians, or more commonly people call it Jacobians, of these. So this is the Jacobians that were referenced at the beginning of the video. And rather than writing this out all the time, we usually just use the notation partial x comma y over partial u comma v. Right? And so the putting x comma y together over u comma v together really is telling us that we're talking about the determinant of that matrix. Oh, I should not have the delta u's and the delta v's in there. Sorry. Those should be gone. Ignore those. Okay. So when we actually plug this into the integral, what does this mean? Well, so our original integral, if we're integrating in terms of a region R in terms of xy of some function dA, well, so we're going to make the change of variables, and so x is turning into, for x we're plugging in x of uv, for y we're plugging in y of uv. I wrote r sub uv just to recognize that we're treating the region now in terms of u and v rather than in terms of x and y. And then dA is being transformed into the absolute value of the Jacobian times du dv. And again, I put in du dv, it could be dv du, depending on what integral you want to do first, which integral you want to do first, which variable you want to integrate in terms of first. So du dv or dv du. Doesn't really matter. Okay. But this Jacobian here, this is sort of playing the role of when we go from dx to du, what that factor is that we have to bring in to make that substitution. And in fact, this idea of Jacobians, this is really deep down, this is the exact same thing in theory of what we do when we go from dx to du in one dimension. Really, in terms of if we went through and did the whole thing, there'd be a whole lot more inverse functions going on. And so I don't think that would be all that illuminating, and it might be fairly confusing to go through. But deep down, this is what's happening when we do a U substitution. This same factor is actually, the same type of factor actually gets introduced. Okay, so I want to close this out. We've actually already done a change of variables when we talked about polar coordinates. And so let's calculate out what this Jacobian for polar coordinates is when we do the change from polar coordinates. Right? And so remember our change of variables for polar coordinates, when we're going from x, y to r theta, x becomes r cosine theta, y becomes r sine theta. Right? So the partial of x in terms of r is going to be just cosine theta. The partial of x in terms of, let's do partial of y in terms of r. That's just going to be sine theta. if we do the partial of x in terms of theta, so r is a constant, and then derivative of cosine is minus sine theta. And when we do the partial of y in terms of theta, we get r, and the derivative of sine is cosine. Okay. So our Jacobian, going from xy to r theta, so this is the determinant of, just writing these in, so partial of x in terms of r is cosine theta, partial of y in terms of r is sine theta, partial of x in terms of theta is minus r sine theta, partial of y in terms of theta is positive r cosine theta. One thing I should note, that in terms of because we're taking this determinant, it's perfectly fine to swap those two entries. That's not going to change the determinant at all. If we swap the other two, that would change the sign of the determinant. But if we swap the two diagonals going upwards, that doesn't change anything. So just in case you ever swap these two, it's not really causing any difference. And so then doing the determinant, multiplying this diagonal, we get r cosine squared theta, and then we have to subtract off the product of the other diagonal, but that's going to be minus r sine squared theta. And so really it's r times cosine squared theta plus sine squared theta, and that's just 1. So the Jacobian here is equal to r. And if you think back, what's dA in terms of polar coordinates? Well, dA in polar is equal to r dr d theta. That r right there is the Jacobian. And in fact, the calculation we did to get r, that was exactly the same calculation as doing the Jacobian. Okay, and so treating this change of variables, like the general way in terms of Jacobians, we get exactly the same thing as what we did by hand. So that is all I have for you for this video. I will see you again soon.